Good afternoon, everyone. My name is Mitch McLeod, the Director of Business Development at Lanmark. Today, we're going to have an overview of defect assessment for pipeline integrity management. This will be the first in a series of webinars we'll be offered on this topic. We will be doing a deep dive in future sessions. If you have any questions, there will be opportunities during the presentation where you can ask a question in the meeting chat. If specific to your program, you can also follow up with Merdad after. Our subject matter experts today, Merdad Palisi, EIT, has a PhD in structural engineering. He's a stress engineer with research experience in finite element analysis and computational modeling for pipeline integrity, pressure vessel design, and vibration analysis. He specializes in nonlinear mechanics, and this includes plasticity, damage, and fracture. Abacus and automation with Python, subroutines, and development of practical data-driven assessment workflows. Also, we have Jaspreet Hoti, principal engineer, 20 years of experience in mechanical engineer and project management, has extensive experience with forensic failure analysis of assets in the oil and gas industry, specialized experience in evaluating asset integrity and fitness for service, specialized experience performing life assessment studies involving fatigue and fracture. A wealth of experience with industry codes including CSA, Z662, B31X, API, and PHMSA. Also, we have Michael Yu, professional engineer and project manager. Mr. Yu work experience ranges from designing overall processing plants to solving highly technical mechanical engineering problems. His wide range of skills extends to pipeline design, facilities design, project management, and coordination of field assessments and failure analysis. He has experience with TC Energy, ONIAC, and Synovus Energy. And with that, I'll turn it over to Merdad and our integrity team.
Thank you very much, Mitch, for the introduction. Good afternoon, everyone. Thank you for joining us today. This webinar is the first session for a series on pipeline defect assessment. Today, we will provide a high-level overview of our defect assessment program. In future sessions, we will focus on specific imperfection types, their assessment, and management. So I'll start with an overview of pipeline integrity management, or PIM, and its key elements. Then I'll introduce the imperfection types covered in our program, explain their causes, assessment methods, categorization, and management at a high level. Next, I'll walk you through the process for 2 Level 3 FEA assessment, pipelines with corrosion and dents. And finally, I'll present the typical deliverables for pipeline defect assessment projects and briefly introduce other stress engineering services we support. So as we all know, transmission pipelines provide a safe and efficient way to transport energy products over long distances. This network continues to expand and diversify with emerging services such as hydrogen blends, carbon dioxide, and biofuel transportation. As pipelines age and operating conditions change, threats can develop and grow over time. In case of transmission pipelines, failures are rare, but even a single event can have serious consequences, affecting public safety, the environment, business, and reputation. So in order to prevent failures, operators implement something called Pipeline Integrity Management, or PIM program. The images shown here are related to 2010 San Bruno incident, where natural gas pipeline ruptured in a populated area. This was because of a crack in a seam weld that grew unstably during a pressure excursion, caused a major explosion, and tragically killed 8 people. So we want to prevent incidents like this to happen. So what is pipeline integrity management, or PIM? This is a structured process to develop, implement, measure, and manage pipeline integrity. It is done through assessment, investigation, mitigation, and risk prevention. And we want to make sure that we have a safe and reliable service. A typical PIM, as is shown in the figure, includes 5 essential elements: identification, assessment, mitigation, monitoring, and prevention. So let's take a look at each one of these elements in some more detail. The first element is identification. This is where imperfections are detected and sized. The main identification method for imperfections on transmission pipelines is inline inspection, or ILI, in which an inspection device with various technologies travels through the pipeline and identifies threads. Different ILI technologies are used to detect different imperfection types. Here in this image, we have some examples of these technologies. So caliper tools, they are used for measuring pipe inside geometry. They can detect deformation anomalies. We have magnetic flux leakage, or MFL, which is used to detect metal loss. Ultrasonic or UT tools measure wall thickness. They are used for metal loss detection, and some of the models for crack detection. And we have electromagnetic tools that are mainly used for crack detection. ILI tools have practical limitations. They may not be able to pass through tight bends depending on the configuration of the tool. In addition, the ILI technologies, they have detection and sizing uncertainties. So here we have 2 examples of the technologies for corrosion. MFLA is used for detecting and sizing metal loss, such as corrosion and pitting. IEC provides high-resolution detection for internal metal loss. Both these technologies, they have a minimum bend radius of about 1.5 times outside diameter. MFLA depth sizing is generally about 10 to 15% of the wall thickness. IEC depth sizing is about 1.3 millimeter. Both technologies, they have a probability of detection of 80%. The next element for PIM is assessment. This is where the collected data is used to make sound engineering decisions. The 3 main types of assessment include consequence, risk, and fitness for service, or FFS assessment. Consequence assessment looks at the potential impacts of a pipeline failure over people, the environment, and operation in general. Risk assessment estimates the overall risk of a pipeline failure by combining the likelihood of that failure with its consequences. And finally, fitness for service, or FFS, checks whether a pipeline with identified imperfections can continue to operate safely under operating conditions. FFS is the focus of this presentation. Here we are using ILI data, operating conditions, and maintenance records to assess immediate and future integrity of the pipeline. This is done typically by estimating the failure pressure and remaining life because of wall thinning or fatigue failure. Next, we have mitigation. This might be required when FFS is showing that an imperfection is unacceptable. After excavation and field inspection, if the defect was present and it was as severe as it shows itself in the ILI data, then a repair should be applied. There are different types of repairs depending on the type of defect and its severity. Common options include pipe replacement, composite sleeves, grinding, and metallic sleeves. Pipe replacement removes the damaged section of the pipe. However, this method requires line outage and it is not preferred. Composite sleeves, they reinforce the pipe by sharing the tube stress, so they can be used for the longitudinal defects. Grinding basically removes the local stress risers over the pipe. And we also have metallic sleeves that are commonly available in two forms. Type A sleeves provide reinforcement, and in type B, we have the sleeve welded to the pipe. This type provides pressure containment, and it is generally used for more severe defects for which we might have leakage. Next, we have monitoring. This is going to be the ongoing follow-up component for integrity management. Operating conditions like pressure, temperature, and flow rates, they can be monitored continuously. But for most integrity threats, the monitoring is performed periodically. This typically is done through repeat ILA runs to identify new imperfections, and we can also track the growth of the known features. There is also non-destructive testing that is used to verify ILA findings, improve sizing accuracy, and at the same time, it could also be used when ILA capabilities are limited. So let's say if we have a girth weld for which we have a high demand of stress or strain, we can do the inspection over that with non-destructive testing. The last element of PIM is prevention. Prevention starts early. One of the things is having a strong quality assurance and quality control during manufacturing and construction. This can help us to reduce defects from the beginning of the line life cycle. Also, during operations, there are activities that we can do, including having an effective inspection program, excavation damage prevention, real-time surveillance, having procedures for repair, response planning, and emergency shutdown systems. Any questions so far? Okay, so next I'm going to talk about the primary imperfection categories that we have in our program. The first feature is corrosion. Corrosion is the most common time-dependent integrity threat for pipelines, especially the ones that are buried. There are two types of corrosion, external and internal. External corrosion is more common. It is driven by electrochemical reactions between the pipe steel and surrounding environment. External corrosion is controlled by coating and sealing. External corrosion starts when the coating degrades or fails. It becomes more severe when CP cannot effectively reach the steel. There is also internal corrosion. It is generally less common in transmission lines, but it can occur when water or deposits accumulate inside the pipe. Next, we have dents. This is going to be an inward plastic deformation of the pipe wall. It is usually caused by external mechanical forces, such as construction activities or third-party excavations. It can also occur when the pipe is forced against a hard object below the pipe, such as rocks or buried debris. Next, we have buckle-type features, including ripple, wrinkle, and buckle. These features are caused by a local compressive load over the pipe. The source of this load could be pipe bending, ground movement, or installation issues. Surface cracks over the pipe body. This is another important feature. One common mechanism here is environmentally assisted cracking, particularly stress corrosion cracking or SCC. Here we have tensile stresses. They are working together with a corrosive environment to initiate and grow cracks. SCC often appears as colonies of parallel cracks oriented perpendicular to the dominant stress direction. So if we take a look at this picture, we have a group of cracks aligned in the longitudinal direction. And perpendicular to that, we have hoop stress that is acting as the driving force. Cracks can also grow by fatigue. This is going to be over the critical locations that we have stress concentration. There is higher levels of stress and strain at this location, and during pressure cycling, cracks can develop and grow over time. And finally, one other category is weld imperfections over seam and girth welds. So here we might have planar flaws such as cracks, undercutting, or lack of fusion. They could also be volumetric flaws like cluster porosity, slag inclusion, or lack of penetration. Weld areas are more susceptible in comparison with the pipe body. This is because the weld and heat affected zone around it, they might have different metallurgy. There might also be residual stresses at these locations if post-weld heat treatment is not performed. The main integrity concern about weld issues is that they might behave like cracks, and under operating conditions, they might grow over time. Any questions so far? So in our program in Canada, we are using CSA Z662, Section 1010, Evaluation of Imperfections, as our basis. This provides the screening limits to us and then directs us to more detailed engineering assessment when those limits are not satisfied. For doing engineering assessment over corrosion, we are using ASME B31G together with the supporting reports and technical papers in this manual. Dents are assessed based on API 1183. API 579 is used for assessment over cracks and weld issues that are behaving like cracks. In order to do this, we are using part 9 in this standard. We are also using Annex 2D here to do level 3 assessment over corrosion. And finally, we have ASME B31.8 supplementary material that is providing us the basis for doing categorization over defects. So there's some consideration when we are performing imperfection assessment. Here I have 3 notes that I go through them one by one. The first thing is we are not assessing features only in their as-found condition. There's some features that are time dependent, let's say corrosion. For these features, it is important that we have an estimation over the groove. This could be done by reviewing the historical ILA data. We might also do like a literature review and come up with a conservative value. After we figure out what is the groove for each one of the features, we should project them to the time for the next ILA inspection. Then we're going to perform FFS. This is going to be performed for both the current and projected condition of the features. Key outputs here include the failure pressure and remaining life. In the case of corrosion, this remaining life is because of wall thinning. And in the case of cracks and dents, it is going to be governed by fatigue failure. Then we're going to have categorization and action planning for each one of the features. So we categorize features as immediate, scheduled, or monitored. Immediate features are the ones that are unacceptable at the current condition. Scheduled features, they are acceptable now, but sometimes in the future, before the next ILA run, they're going to become unacceptable. And then we have monitored features. These are features that are acceptable through the next ILA interval. For immediate and scheduled features, it is important to get the safe excavation pressure. This is going to be a percentage of the failure pressure and the amount of pressure at the time that the field crew are doing the repair over the pipeline. Also, we need the repair method and the specification for that. In the case of scheduled features, We should also provide what is the deadline for doing that repair. So when we are doing imperfection assessment, we are generally using a three-level approach. Level one is screening. Here we are using fast, simple checks based on the feature dimension and operating data. It is basically for screening out low-risk features. Then we have level two assessment, which is going to be more detailed. Here we are using the elaborated data for our features. Let's say in the case of the corrosion, we are using the thickness grids for the corroded area. In the case of the dent, we are using the deformation data, specifically the longitudinal and transverse profiles living through the peak of the dent. And then we have level three assessment. Here we are using numerical methods like finite element analysis. It is used for features that are too complex for doing level one or level two assessment over them, or based on those levels, the feature is unacceptable. So this slide here, it is showing this three-level approach that we are applying at Landmark for doing assessment over different types of imperfections. So as an example, for corrosion assessment, we start with CSA screening. Then we make progress to ASME B31G modified formulation. If the data was available, we can also do an effective area method. If the feature was still failing at the level one, then we can go to level two and do like a R strength or P square modeling over that feature. And even we can also go to level three and do a finite element analysis based on APA 579 Annex 2. So similarly for the rest of the features, we have methods for doing analysis in three levels. Let's say for dent, buckle type features, cracks, and crack-like issues. So in the future webinars, we're going to go through details of these imperfection types and see what is the assessment for each one of them. One thing that I want to mention here is in terms of the commercial softwares, we are using Abacus, FESafe, and iSight for doing finite element analysis. For the case of corrosion, we are using R-Strength Plus and Kappa. And for the cracks and crack-like issues, we are using Kappa and Inspect. We also have our internal Python scripts to assess deformation anomalies and perform CSA screening. So in case of some imperfections, let's say if we have a circumferential pipe body crack, we have a crack-like flow over the girth weld, or we have buckle-type imperfections, the longitudinal stress is going to be the driving force and not the hoof stress. In these cases, it is essential to have an accurate assessment for the stress state at that feature location. This could be done using our AutoPipe, or at the same time, we can also use our internal pipeline stress analysis tool. Our internal tool is a Abacus Python script. It builds the pipeline configuration directly from ALA coordinates. We are using pipe and elbow elements, plasticity and nonlinear geometry is included. And we can also include varying pipe soil interaction if that data is available. Flowcharts like this, they can translate level 1 to level 3 framework into practical assessment steps. Here, the flowchart is related to corrosion. For the first column, we have the immediate integrity assessment. We're going to do a projection over the feature and do the future integrity assessment. This is one other flowchart. This one is related to dents. So the time that we have a feature that is unacceptable, no matter what level of analysis we are applying over it, then we can use CSA Z662 table 10.2 to select an appropriate permanent repair method. The table here is just... Yes.
We have a question, is that, is it possible to reduce corrosion in these pipes by using caustic?
Sorry, can you say that again, please? Your
No.
voice come on.
Is it possible to reduce corrosion in these pipes by using caustic?
That may be a question that we'll have to come back to. This is more of a defect assessment webinar, so I don't have that answer right away, but we can get back if the person shares the detailed contact details.
Okay, thank you.
So the table here, it is just part of the table for CSA Z662, table 10.2. The table is focused on the metal loss defects. In the case of the corrosion, the code allows us to do pipe replacement. We might also apply different types of repair slips. If you're using composite reinforcement, the metal loss should be less than 80% of the nominal wall thickness. For the rest of the metal loss issues like gouges, grooves, or arc burns, we also have the option for grinding, but after grinding, we should make sure that based on B31G modified formulation, we have enough wall thickness remain. We can also apply sleeves, but in the case of the steel reinforcement, type A, and composite reinforcement, we should have the stress concentrator. We should grind the stress concentrator. This is another part of that table. This part is related to dents. Any other questions so far? Okay, so next I'm going to talk about two level 3 assessment. This is going to be for corrosion and dents. We're going to focus on the general workflow and also some technical considerations. So let's start with the assessment for corrosion. In the case of corrosion, CSA Z662 and ASME B31G, they're just useful for doing level 1 or level 2 assessment. Actually, in ASME B31G, it provides some general guidelines for doing level 3 assessment, but it is not something detailed or step-by-step. So because of this, we are adapting the stress analysis framework in API 579 Annex 2D for doing level 3 assessment over corrosion. It is important to mention this code itself is based on ASME Boiler Pressure Vessel Code, Section 8, Division 2, Part 5. And actually, this is the code that is used for design by analysis over pressure vessels. So if we have a pressure vessel with some complexity in its geometry or loading condition, this is the code that is used to doing design over those type of structures. One other important thing here is that the approach in Annex 2D, it is not just limited to corrosion. It can be used for many type of imperfections. Actually, in the next slide, I'm going to show you one example, which is related to shell distortion. But generally, the steps going to be the same the time that we are doing analysis over corrosion. So what we are checking inside API 579 Annex 2D. The checks include protection against plastic collapse and buckling. This is going to be for ensuring the overall stability of the structure. We're going to do assessment for checking the local failure, and also for structures that are subjected to pressure or temperature cycling, we're going to do fatigue and ratcheting assessment. Depending on the failure mode, we might use elastic, limit state, and elastoplastic analysis. In elastic analysis, we have linear elastic material behavior. Nonlinear geometry is not included in our analysis. The only exception here is buckling analysis. For buckling analysis, we're gonna activate some imperfection modes into our structure. So then we're going to have nonlinear geometry activated at the start of the analysis before doing the buckling analysis. Then we've got limit state analysis. Here we're going to have elastic, perfectly plastic material behavior. nonlinear geometry not included here. And actually for local failure, we don't have limit state analysis. And finally, we got elastoplastic analysis. This is going to be the most advanced method for doing finite element analysis over defects. Here we have the plasticity of the material. We're going to also include the strain hardening in our plasticity model. Nonlinear geometry here is activated. And one big advantage of this type of analysis is that it is giving us realistic displacement field. So basically, we can take a look at the contours for displacement, also strain and stress, and get some understanding about the structure under the applied loads. So let's go through one example. This is an example in APA 579, example problem manual. This is example 7 in section 8. It is actually added to the book recently. It is illustrating the main steps for doing an elastoplastic analysis using Annex 2D. The structure that we have here is a vertical pressure vessel. It is subjected to internal and external pressure. We also have dead load, and there is also wind applied to the structure. This structure contains some shell distortion, and we're going to use Annex 2D to make sure that the structure is safe. So the first step for doing this type of analysis is to create the CAD geometry in the finite element software that we have it here. And then actually we're going to do discretization over this model. So we're going to have a meshing applied over this geometry. The time that we have that discretization, now we can model the imperfection. So let's say in the case of the shell distortion, we can do this by adjusting the nodal coordinates in the input file in Abacus. So basically the input file in Abacus, it is a text file. We can go through that text file through scripting and change the coordinates of the nodes. And this way we can have shell distortion applied over a structure. In the case of the corrosion, if we are using shell elements, the process is going to be easier. We're going to apply something called map fields over the nodal thicknesses. So basically we have a shell model. The wall thickness for that model is varying for each one of the shell elements, and it is representing the ILA data. So after we did the modeling for the geometry, discretized it, applied the imperfections, and applied the boundary conditions, now we can go and do those checks one by one. The first check that we have is protection against plastic collapse. So what we do is we go into table 2D3. This is going to give us the load combinations and factors for elastoplastic analysis. We go into the global criteria. Here we have two load cases that are relevant to our structure. So one is for internal pressure and gravity. The other one is for the time that we also have wind load applied to the structure. We apply these loads over the structure, and then two things can happen. When we are running our analysis, we might get convergence, which means that our structure is safe against plastic collapse, and we might get divergence. If we got divergence and we are sure that every setting in our model is correct, then that could be an indication that the structure is not able to tolerate that level of loading. The second check is for buckling collapse. If we are doing linear analysis, this is going to be very different from plastic collapse. But in the case of the elastoplastic analysis, we are basically doing the same procedure. The only difference here is that for buckling analysis, we are applying the load cases that are producing compressive stresses inside the structure. So for this example, we have the same load combinations, but instead of internal pressure, we're going to apply external pressure. So finally, we got the check against the local failure. Here again in table 2D3, we're going to have relevant load combination. We're going to apply this load combination over the structure. And then we're going to get different principal stresses, von Mises stress, and equivalent plastic strain. And based on these variables, we're going to have a calculation for a strain-based failure limit. So I'm going to go into details for what is this limit. But for now, we're going to do the calculation for that limit at every point in our model. We're going to get the maximum value. If the maximum value was less than 1, that means our structure is safe against local failure. But what is that strain ratio? That's strain-based failure criteria. It is a strain ratio. It is basically a demand divided by capacity. The demand is equivalent plastic strain. Capacity is something called limiting strain. So let's go through the calculation for an example, see how this is done. So the first thing is we should know what type of material we are working with, what is the yield stress and tensile stress for that material. Actually, we need the ratio of yield to tensile stresses. We also have some outputs from our finite element software. We've got the principal stresses and also the equivalent plastic strain. So what we do is we calculate the average stress, the von Mises stress, and then we calculate the ratio of the average stress to von Mises stress. Actually, this is an important variable. It is called the stress triaxiality. In many failure criteria, you might see this ratio. So after those calculations, we're going to get some material properties. We go into table 5.7 in ASME boiler pressure vessel code, section 8, division 2. We are getting the material constants. This is the limiting strain, but this is just for the case of uniaxial stress case. So if we are putting it into this relation, we're kind of generalizing it for the multi-axial stress state that we are against. So we get the limiting strain, and then we're going to have equivalent plastic strain divided by limiting strain. If the value was less than 1, that means that point in the structure is okay against local failure. Any questions so far? So next, I'm going to talk about the level 3 assessment for dents. In the case of dents, we have 2 main steps. The first step is dent strain assessment. Basically, we want to have a quantification for the amount of damage in that indented area, the time that we had the indentation. And actually, the second part is doing FFS assessment. This is going to be for the fatigue failure for the dent. If in the first step, we got like a severe dent, then probably we're going to have crack inside that dent, and we should kind of be mindful for the fatigue life and failure pressure of that crack. We can have some assumptions over the dimension of that crack, but probably the best way is to do inspection over that area, figure out what is the, do we have cracks there, and what is the dimensions of those cracks, and then continue with the assessment. So today I'm going to go into details for the dent strain assessment. Hopefully in the future, we've got webinars about talking about dents and also cracks separately. So here we've got 2 main steps. The first step is simulation of the denting process. Actually, this is going to be the most challenging step for doing analysis over dents. So what we do here is we have the CAD geometry. We also do discretization over it. It is like a good practice to have refined mesh at the places that we have contact between our indentor and the pipe. Next step, we're going to define an indentor. We're going to define a contact between the exterior surface of the pipe and the indentor. And then we're going to apply displacement over this indentor. After we are finished with the indentation process, we're going to have the pipe pressurized. So what we do is we are applying some full pressure cycles. This is basically because the time that we have in reality, because of the pressure fluctuations over the indented pipe, we're going to have some plasticity formed at some locations. And with this full pressure cycles, we're going to capture those plasticity. At the last step, we're going to just increase the pressure from 0 to the pressure at which ILA measurement was performed. So what is the challenge here? The challenge is that the time that we are finished with our modeling, we should do a comparison between our simulation and the ILA data. If our simulation is not matched reasonably over the ILA data, then we're going to have to go back to this step. We're going to change the dimensions, the shape, and the movement of the indentor, and repeat this process till the time that we get like a reasonable match. So the next step, we've got the calculation for we're going to do a quantification over the amount of damage during the indentation. This is going to be done with, actually there is more measurements in API 1183. The one that we have here is ductile failure damage indicator, or DFDA. So DFDA, just like the strain-based failure criteria for corrosion, this is going to be also a demand divided by a capacity. The demand is similarly equivalent plastic strain. The capacity is something called fracture strain. Fracture strain is coming from this relationship. As you can see it here, we have some consideration for the stress triaxiality. And we also have this epsilon 0. This is the critical true strain at the start of the crack initiation. Its value is between 0.3 and 0.6, according to API 1183. At the same time, we can also use this relation to figure it out if we have the material information. This true strain is associated with the ultimate stress. This is going to be the last value for the true strain in the uniaxial material test. So if we get the average of these two values, this is going to give us epsilon 0. So what is happening in this relation here? Actually, I have two examples, one biaxial tension case and one compression case. So if we go through the calculations, we can see that for the fracture strain, we are getting much more capacity in the case of the compression, and therefore the amount of damage is much less. So this is something that is consistent with the mechanism for ductile failure. Ductile failure involves initiation, groove, and coalliance of microvoids, and this situation is more susceptible to happen for tensile stresses. So basically, in this relationship, we are kind of taking care of that note about the stress state. So in terms of the deliverables, we're going to have a preliminary assessment. This is going to be for the time that we have ILA once completed. So what we do is we're going to have the ILA data collected and reviewed. Then we're going to have an estimation for the corrosion roof rate. This could be based on literature review. We might use a method like half-life, or we might also review the historical ILA data to get this value. Then we're going to have calculation for the failure pressure and remaining life. For different features, the remaining life is for different types of failures. It might be because of leak or burst in the case of corrosion, or in the case of crack and dents, it might be because of the fatigue failure. So some of the features that we do assessment over them, they're going to be in a critical situation. So then we're going to have those features targeted for doing dig investigation. In addition, we're going to have a pipeline risk assessment. This is going to be with subject matter experts. There's going to be a lot of parameters to consider for this risk assessment, as you can see it here. For the features that are unacceptable, we're going to have a preliminary repair method, and also we're going to define the project constraints. And then we have a preparation for the dig sheets and dig work package. So what is in the dig sheet? In the dig sheet, we had the excavation site location, the feature description, the feature location, and pipe joint identification. Here we've got information like the length for the joint that we have the flow inside it, and also the adjacent, as well as the wall thickness. So this information is very useful for the crew that want to do the repair. They can check the length, they can check the wall thickness, make sure that they are digging the right spots. There is also a dig work package. Here we're going to have the pipeline information, the restricted pressure. This is going to be a percentage of the failure pressure. It is for the time that the crew are doing the field inspection and they're doing the repair. We also have the identification for the target feature. What was the recommended repair methodology, the instructions for doing the field inspection, and also the requirements for safety and emergency response. So the picture that we are seeing it here, on the x-axis we have chain age. For the y-axis we have the clock position. Here we can see the location for the gear floats. So here basically we are kind of taking over this segment of the pipe. We can see different features that we have over this segment of the pipe. Which one was the critical feature that we have? This one was our targeted feature. And also, what is our preliminary repair method over this, the start of the sleeve, the end of the sleeve, and also the specifications for that sleeve. So after the field inspection is finished, then we're going to have another set of integrity assessment. So this time we're going to collect and review the field inspection reports, and we're going to have a correlation between the field entity results and ALA reported anomalies. So basically, we want to verify the feature locations and their severity. Let's say in this graph, the blue is related to ALA data, the red is related to the field inspection. So as we can see, the locations of the features is a little bit mismatched. We also have a lot of small features that ALA one detected. We didn't see those in the NDT. And there is also a seam belt non-fusion that we cited in the NDT, and this wasn't in the ALA data because we didn't have the technology to detect this type of imperfection. And there is also a unity plot like this. On the x-axis we have the ALA data, and the y-axis we have the data from the NDT. If the ALA data was working ideally, we had everything over this unity line. But as we can see, ALA data is overcalling some of the features. If we are in this zone, that is undercalling the features, probably the feature is going to be more critical than ALA data is telling us. We might also have features over x-axis. This is going to be the features that ALA data detected, but we didn't have them in the NDT. And here, there's going to be for the features that the NDT detected, and probably we didn't have that technology, or ALA data kind of missed over those features. So this way, we're going to have a correlation between field NDT and ALA reported anomalies. Then, if it was required, if the features were in a more critical situation that ALA data was sharing it, then we're going to have recalculation for the failure pressure and remaining life. And then we're going to do the finalization for the repair methodology. what is the type of sleeves that we want to use, what is the landing zone for those sleeves. And then we have the post repair documentation and the final risk assessment. This is done after the field repairs are finished with the crew that are working over the pipeline. So we're going to create drawings and documents that are required for recording the repair. Then there's going to be the determination for the next ILA run date and also technologies to use in that ILA run. So in the field inspection, we might see some features like cracks, and we don't have tools for them in our previous ILA runs. It might be a good idea to have, let's say, tools like shear wave, ultrasonic, some advanced models of ultrasonic for detecting cracks over that line. And then we're going to have the final pipeline risk assessment. So we did assessment over the pipeline, we did the inspection, we did the mitigations over the pipeline, and probably our risk is going to be lower at this stage. And then we complete the management of change process. So in terms of Landmark, our team, our stress engineering team, is supporting both facility and pipeline projects. On the pipeline side, we can do pipeline stress analysis, defect assessment, as I mentioned today. We can also do elevated temperature assessment, geohazard and hydrohazard assessment, and some supplementary calculations. In the case of the facilities, we can do piping stress analysis. We can do defect assessment for piping system, pressure vessels, and the storage tanks. Dynamic analysis, including modal, harmonic, dynamic explicit and implicit. Piping design for services with very low or high temperature, and some supplementary calculations. So I would like to thank you all for joining this session. If you have any questions, we would be happy to answer. At the same time, you can also reach out to us, and we would be happy to go into further discussion for any of the topics in today's presentation.
Hey, thanks everyone for attending. As Mehrdad said, is that please reach out directly if you have specific projects regarding your program. We'll also be making this presentation available on YouTube on our channel there. So if you would like to share with any of your coworkers, let me know and I can send you the link for that. Our next webinar will be on June 16th, and it'll focus on the civil side of our business and regarding structural analysis and piling design. And have a great day. May the 4th be with everyone. Thanks.
Yeah.